let's go ahead and take a look at what kinds of particles can be lost or gained by atoms in a nuclear reaction. So the first kind of particle that we have is called the alpha particle. And basically all an alpha particle is a helium atom, essentially. We actually show this through the symbol He with an atomic number of 2 and a mass number of 4, or simply as just this Greek letter for alpha. It says an alpha particles are large and slow moving, and they can actually be stopped with something as small as a piece of paper. So take a look at this reaction here. I've got uranium-238. Well, I know that this is uranium-238 because here's my symbol for my element. Here's my atomic number down here, and then my mass number up here. If we remember way back from the beginning of the year, I remember that the mass number is the number of protons plus the number of neutrons. Well, if this is going to lose an alpha particle, I'm going to lose the number 4 from my mass number, and I'm going to lose the number 2 from my atomic number. And so what that ends up giving me is if I lose 4 from here, it gives me 234. If I lose 2 from here, it gives me 90. And so we can actually see where we form a brand new element. So I start with this large element here. I lose the 2 protons and 2 neutrons, or the alpha particle, and then that's what gives me this new nucleus and an alpha particle. Another kind of particle that we can lose is called a beta particle. And a beta particle, it says a beta emission results when the nucleus converts a neutron into a proton and an electron. So we take a neutron and we convert it into those two pieces, the proton and the electron. We can represent this with this letter B or this symbol right here. And this symbol is going to be the better symbol that we can use when we're doing a nuclear reaction that we're actually writing out, because I can, once again, I can add the 0 to this number, and I still see that I still have the same mass number, and I can add this -1 to this. So if this 53 loses a -1, minus a negative is like adding, and so the atomic number ends up going to 54. So this is like a basic addition reaction that we can do that'll just give us our new numbers. We can also have positron emission. Positron is very similar to beta emission. It's going to be represented with this B plus or this symbol right here. And so what's actually happening is we're converting a proton into a neutron and a positron. And so we can use this symbol to add into our reaction to figure out what our new element is going to be. It says that wood or glass can block a positron emission. Each one of these has an amount of energy that's associated with it, and we're actually going to take a look in a few minutes about what that energy is called and how that energy is released. The next type of decay is called electron capture. This one is the only one that has the particle that's being decayed on the reactant side. So what we're actually doing here is we are sucking in this particle into the nucleus to form our new product. So we can describe the energy that's being lost as gamma radiation. So when we go back here and look at all of these that are releasing energy, that one's releasing energy, this one's releasing energy, all of that energy is being released in the form of gamma radiation. It says gamma radiation has no mass or charge. All it is electromagnetic waves. These electromagnetic waves have a lot of energy. It says because they have no mass, gamma radiation is able to penetrate most substances. So therefore, we have to block gamma radiation with lead. Okay, very, very thick sheets of lead. That's why when you go to the dentist and you get an x-ray done, they put that really heavy blanket on you. That's a lead blanket that they're putting on you to prevent the radiation from going into your body. So we can see that alpha particles can be blocked with paper. Beta particles and positrons can be blocked with wood or glass. And lastly, gamma radiation can penetrate all of that and must be stopped with a block of lead. So now we're going to take a look at balancing nuclear reactions. when I'm looking into balancing a nuclear reaction, I have to remember my nuclear symbol. I have to remember that this is the symbol for the element, this is the atomic number at the bottom left, and this is the mass number at the top left. Now, we're not going to be terribly interested in this stuff on the right-hand side. We're mainly going to be focused on the mass number and the atomic number. So let's go ahead and take a look at the equation for the alpha decay of polonium-214. Now, these problems are as easy as writing a basic addition problem. So I know that if I have polonium 214, this 214 is the mass number, so it goes top left. The atomic number for polonium, which is 84, goes bottom left. Now, since this is alpha decay, I know that I'm releasing an alpha particle, which looks like this, 4 and 2, He. And I'm going to get something as my product. Well, now I just have to ask myself, 4 plus what gets me 214? Of course, that number is 210. 2 plus what gets me 84? Well, of course, that number would be 82. And so now I need to see what element is associated with an atomic number of 82, which of course would be lead. So this is going to be the new atom that I'm going to get. So now let's go ahead and take a look at the reaction for the beta decay of bismuth 210. So bismuth 210 is represented like this. I've got bismuth, my mass number 210 on top. My atomic number for bismuth is 83. This is undergoing beta decay. So what's going to happen then is it's going to lose an electron or a beta particle. And so what we would say then is I'm going to say 0 plus what number gives me 210? Well, of course, that's going to be 210. Negative 1 plus what number gives me 83? And of course, that is going to be 84. So now I want to see what element is associated with element number 84, and that's going to be polonium. So that's how we're going to do these types of problems. Let's go ahead and do the next two together as well. Positron emission for arsenic 70. Well, arsenic 70, I've got AS for arsenic. I have 70 for my mass number. The atomic number of arsenic is 33. And so when this undergoes positron emission, I'm going to lose a positron particle, which looks like this. And so now, same thing. 0 plus what gives me 70? 1 plus what gives me 33? And so now I see what element is associated with element number 32, and that's going to be germanium. So now, one last one. Let's go ahead and take a look at vanadium 70. So I've got vanadium 70. That's element number 23. Now this one's undergoing electron capture. Remember, electron capture is the only one which shows the particle on the reactant side. So this is going to capture this electron particle. And so when it does, now I'm going to do my basic math here. 70 plus 0 is 70. 23 plus negative 1 is 22. And the element associated with a number 22 is titanium. So that's how these problems are going to work. Example 15-5 just wants you to decide what kind of particle goes in place here. It's already in there for you. Basically, all you have to do is decide, okay, once again, it's a basic math sort of deal where you say 10 plus what gives you 10? Oh, it's 0. 5 plus what gives you 4? Oh, of course, it's negative 1. And that's how you're going to be able to figure out the type of particle. We have one more topic to discuss, and that is substances actually decaying, which is going to be the topic of half-life. And half-life is the time that it takes for 1/2 of your original radioactive substance to decrease by 1/2 of its amount. Okay, so if you start with 10 grams, how long does it take to get down to 5 grams? And then how long does it take to get to 2.5? And then to 1.25, and so on and so forth. Okay, that's what we mean by half-life. So after 2 half-lives, you only have 1/4 of the original amount left. After 3 half-lives, you have 1/8 of the original amount left, so on and so forth. So let's take a look at these two problems. In example 15-6, we have phosphorus 32 has a half-life of 14 days. It says that we're going to begin with 100 grams of this sample, and it wants to know how much phosphorus 32 remains after 42 days. Well, if I am going for 42 days and my half-life is 14 days, I can divide 42 by 14 and see that I undergo 3 half-lives. So what I'm going to do is I'm going to take 100 and divide it by 2. That's my first half-life. I divide it by 2 again, there's my second half-life. I divide it by 2 again, there's my third half-life. So I can literally put on my calculator 100 divided by 2, enter, divided by 2, enter, divided by 2, enter. And I get that my answer is 12.5 grams. For the next problem, it says the half-life of iodine 25 is 60 days. We're starting off with 12 grams, so 12 grams. I know the half-life is 60 days, and I am going to wait for 360 days. So 360 divided by 60 is 6 days, or excuse me, 6 half-lives. So I'm literally going to divide this by 2 6 times. So 12 divided by 2, divided by 2 again, that's 2, 3, 4, 5, 6. So I can type that into my calculator, and when I do, I'm going to get an amount of 0.1875 grams. And that's how half-life works.